Welcome to this walkthrough of LeetCode problem number 1723, find minimum time to finish all jobs. In this video, we will analyze the problem, break it down into manageable steps, and explore an efficient approach to solve it. Let's get started. In this problem, we need to distribute a set of jobs among a given number of workers in such a way that the maximum working time of any individual worker is minimized. The input consists of an array jobs, where each element represents the time required to complete a specific job, and an integer k, which is the number of workers available. Each worker can handle at most one job at a time, and our goal is to assign the jobs so that no single worker is overloaded compared to the others. The output will be a single integer, which represents the minimum possible value of the maximum working time among all workers. For example, if we have 3 jobs and 3 workers, we can assign each job to a different worker, and the maximum time any worker spends will simply be the time of the longest job assigned to them. Let's look at the first example. Here, the input is jobs equals 3, 2, 3, and k equals 3, meaning there are 3 jobs and 3 workers. To minimize the maximum working time, we can assign each job to a different worker. For instance, assign job 0, which takes 3 units of time, to worker 1, job 1, which takes 2 units of time, to worker 2, and job 2, which takes 3 units of time, to worker 3. In this case, the maximum working time among the workers is 3, as no worker handles more than one job. Thus, the output is 3. In the second example, we have jobs equals 1, 2, 4, 7, 8, and k equals 2. Here, there are 5 jobs and only 2 workers. One way to distribute the jobs is to assign jobs 7, 4, to worker 1, which gives a total time of 11 for that worker, and jobs 8, 2, 1, to worker 2, which also totals 11. This ensures that the workload is balanced, and the maximum working time among the workers is 11. Therefore, the output for this example is 11. Finally, in the third example, the input is jobs equals 5, 5, 5, 5, and k equals 2. Here, there are 4 jobs and 2 workers. To minimize the maximum working time, we can divide the jobs evenly between the 2 workers. For instance, assign 2 jobs, 5, 5, to worker 1, resulting in a total time of 10, and the remaining 2 jobs, 5, 5, to worker 2, also resulting in a total time of 10. Since both workers have the same workload, the maximum working time among them is 10. Thus, the output is 10. Now, it's important to consider certain constraints and edge cases. For example, if there's only one worker, they must handle all jobs, so the output would simply be the sum of all job times. On the other hand, if there are more workers than jobs, each worker can handle at most one job, and the output would be the largest job time. Additionally, if all jobs require the same amount of time, the jobs can be evenly distributed among workers, making the output equal to the sum of one subset of jobs. To approach this problem, we first need to understand the goal, minimizing the maximum workload among k workers while distributing all the jobs in the jobs array. One of the simplest solutions to consider is the brute force approach. Here, we generate all possible ways to assign n jobs to k workers and calculate the workload for each distribution. The smallest maximum workload across all these possibilities would be our answer. However, the number of combinations grows exponentially, specifically k(n), making this approach computationally infeasible for larger inputs. A more refined approach is backtracking with pruning. This method involves incrementally assigning jobs to workers while pruning any branches where a worker's workload exceeds the smallest maximum workload we've found so far. While this significantly reduces the search space compared to brute force, it still relies on exploring a large number of combinations, which becomes impractical as the input size grows. These initial approaches help build intuition but fall short in terms of scalability for larger problem instances. Now, let's consider a more optimized strategy, a combination of binary search and a greedy feasibility check. The key insight here is that the minimum-maximum workload must lie between 2 values, the largest job in the jobs array, which is the smallest possible maximum workload, and the sum of all jobs, which represents the scenario where one worker handles everything. Using binary search, we can narrow down this range efficiently. For each candidate maximum workload, or mid, we check if it is feasible to distribute the jobs such that no worker's workload exceeds mid. This feasibility check can be implemented using a greedy algorithm, typically with backtracking or depth-first search, to assign jobs while respecting the workload limit. If the distribution is valid, we adjust our binary search range to smaller values, aiming to minimize further. If not, we increase mid. The combination of binary search, which operates logarithmically over the range, and the pruning inherent in the greedy feasibility check makes this approach significantly more efficient than the previous methods. This strategy is both intuitive and powerful, which is why it was chosen for the problem. What makes this approach particularly effective are a few key observations. First, the range of possible maximum workloads is naturally bounded by the largest job and the sum of all jobs. Binary search allows us to systematically and efficiently narrow this range. Second, the feasibility check leverages problem structure by assigning larger jobs first, ensuring that we quickly identify invalid distributions and prune unnecessary computations. Compared to backtracking with pruning, which improves over brute force but still struggles with scaling, binary search drastically reduces the number of possibilities we need to explore. While the feasibility check itself may seem computationally expensive, the reduction in the search space more than compensates for this cost. In terms of complexity, the binary search contributes a logarithmic factor, and the feasibility check involves distributing the jobs, which scales well in practice. Overall, this approach strikes an excellent balance between simplicity and efficiency. By combining the strengths of binary search and greedy algorithms, we achieve a method that is both scalable and effective within the constraints of the problem. The problem find minimum time to finish all jobs is a classic workload balancing challenge. Here, we need to assign n jobs, where each job has a specific duration, to k workers in such a way that the maximum workload assigned to any worker is minimized. This essentially means we are trying to distribute the jobs as evenly as possible, but we must ensure that no worker's workload exceeds a certain threshold. To solve this, we use a combination of binary search and backtracking. First, we define the search space for the answer. The lower bound, low, is the time taken by the longest job because no worker can handle less than that. The upper bound, high, is the total sum of all job times, which represents the unrealistic scenario where one worker handles all jobs. The optimal solution must lie between these bounds, and our task is to find it efficiently. Next, we perform a binary search to pinpoint the smallest maximum workload possible. For each midpoint value mid, which represents a candidate for the maximum workload threshold, we check if it is feasible to distribute all jobs among the workers without exceeding this threshold. The feasibility check is done using backtracking. This process involves recursively assigning jobs to workers while ensuring that no worker's workload exceeds mid. To optimize this, we start by sorting the jobs in descending order, which allows us to assign larger jobs first. This strategy minimizes the likelihood of running into infeasible configurations early, effectively pruning the search space. During the recursive assignment, if a job exceeds the mid limit for a worker, we backtrack and try a different allocation. Additionally, if a worker's workload is 0 after a round of assignments, we stop exploring further configurations for that branch since it would lead to redundant results. If we can assign all jobs under the mid threshold, then mid is feasible, otherwise, it is not. Once we determine the feasibility of a given mid, we use this result to adjust our binary search bounds. If the current mid value is feasible, it means we can possibly minimize the maximum workload further, so we update the upper bound to mid 1. On the other hand, if mid is not feasible, we need to increase the threshold and therefore set the lower bound to mid plus 1. This process continues until the lower bound exceeds the upper bound, at which point the binary search terminates. The value stored in low at the end represents the smallest maximum workload that can be achieved while satisfying all constraints. This algorithm works efficiently because it leverages two key insights. The first is using binary search on the result space, which drastically narrows down the range of potential solutions. Instead of iterating through all possible workloads, binary search eliminates large chunks of invalid options with each step. The second insight is the use of backtracking with pruning. Sorting the jobs in descending order and skipping redundant configurations, such as when a worker's workload remains 0, significantly reduces the number of recursive calls needed. Together, these techniques ensure that the solution is both optimal and computationally efficient, systematically validating feasible configurations while discarding invalid ones. The algorithm relies on a few critical data structures. First, we use an array to store the job durations. Sorting this array in descending order helps optimize the backtracking process by assigning larger jobs first, which reduces the likelihood of exploring infeasible configurations. Second, we maintain a list to track the current workload of each worker during the backtracking process. This allows us to quickly check and update the workload of workers as jobs are assigned, ensuring that the constraints on maximum workload are upheld. Analyzing the complexity of this algorithm, we start with the time required to sort the jobs array, which is O, n log n, where n is the number of jobs. The binary search itself has a complexity of O, log, sum max, where sum is the total duration of all jobs, and max is the duration of the longest job. The backtracking feasibility check, in the worst case, can take O, k to the power of n, where k is the number of workers. However, in practice, pruning significantly reduces the number of recursive calls, making this step much faster. Combining these, the overall time complexity is approximately O, n log n plus log, sum max, asterisk f, k, n, where f, k, n, represents the reduced backtracking complexity due to pruning. The space complexity is O, n plus k, accounting for the jobs array and the list tracking worker workloads. Let's walk through an example to see the algorithm in action. Consider the input jobs equals 3, 2, 3, and k equals 3. First, we calculate the bounds for binary search. Low is 3, the longest job duration, and high is 8, the sum of all job times. We start with the midpoint mid equals 5 and check feasibility. Assign job 3 to worker 1, job 3 to worker 2, and job 2 to worker 3. This allocation is feasible since no worker exceeds the threshold of 5. We then update the upper bound to high equals 4. Next, we check mid equals 3, but this time, it's not feasible to distribute the jobs without exceeding the threshold. Finally, the binary search converges, and we return low equals 4 as the smallest maximum workload achievable. This example highlights the efficiency of combining binary search with backtracking to systematically arrive at the optimal solution. Here, we define the minimum time required function within a class called solution. This function takes three parameters: jobs, which is a list of integers representing the time each job takes, and k, the number of workers available to distribute these jobs. The goal is to find the minimum time required to complete all jobs when they are distributed optimally among the workers. A helper function, canDistribute, is defined to determine whether it's possible to assign jobs to workers such that no worker exceeds a given maximum workload. This is achieved using a recursive backtracking approach. Inside the backtrack function, we try to assign the current job to each worker, checking if adding the job to their workload keeps it within the allowed limit. If the assignment is valid, we proceed to the next job. If at any point a worker's workload becomes 0, we break early to avoid redundant checks. After defining the helper function, we sort the jobs in descending order to optimize the backtracking process by assigning the larger jobs first. Finally, we initialize a binary search between the maximum single job time and the total sum of all job times to find the minimum possible maximum workload. The function concludes by returning the value of left, which represents the minimum maximum workload that allows all jobs to be distributed among the workers. This result is derived from the binary search process, where we repeatedly narrow the range of possible workloads based on whether the canDistribute function returns true or false for the midpoint of the current range. The binary search ensures that we efficiently arrive at the optimal solution, making the implementation both concise and performant for the problem at hand. Here, we start by importing necessary libraries and defining the solution class. The main method, minimum time required, takes two inputs, an array of job times and the number of workers, k. The goal is to minimize the maximum workload assigned to any worker. First, the jobs array is sorted to make it easier to handle the largest job. We then initialize two bounds, left, which is the largest single job time since no worker can have a workload less than this, and right, which is the total sum of all job times because, in the worst case, one worker might handle all the jobs. Using binary search, the method narrows down the range between left and right. The midpoint, mid, represents a candidate for the minimum maximum workload. If the helper method canDistribute determines that it is feasible to distribute the jobs among the workers within this workload, we adjust the upper bound, right, to mid. Otherwise, we increase the lower bound, left, to mid plus 1. By the end of the loop, left holds the optimal solution. The can-distribute method, defined next, uses a backtracking approach to check if the jobs can be distributed among k workers while keeping their workloads under the specified limit, max workload. The backtrack method is the core of the recursive logic. It attempts to assign jobs to workers one by one, starting from the current job at the index position. If all jobs are assigned successfully, the method returns true. For each worker, it checks if the current job can be added to their workload without exceeding the max workload. If it can, the job is tentatively assigned to that worker, and the method recurses to attempt assigning the next job. If the recursion succeeds, it returns true to indicate a valid distribution. If not, the job is unassigned, and we backtrack to explore other possibilities. Additionally, if a worker has not been assigned any jobs yet, we break out of the loop early because assigning the current job to another unused worker would yield the same result. This optimization reduces unnecessary computations. If no valid assignment is found after testing all workers, the method returns false. This recursive approach ensures that all possible distributions are explored while leveraging optimizations to improve efficiency. To solve this problem, we start by sorting the jobs in descending order, which gives us 3, 3, 2. This ensures that we allocate the largest jobs first, which is a key strategy for minimizing the maximum workload. Next, we initialize the binary search bounds. The left bound is the maximum job time, which is 3, since no worker can be assigned less than the longest individual job. The right bound is the sum of all job times, 8, representing the scenario where one worker takes on every job. We then calculate the midpoint of these bounds, 5, and begin checking if it's feasible to allocate the job such that no worker exceeds this maximum workload. First, we assign the job with time 3 to worker 1, resulting in workloads of 3, 0, 0. Next, we assign the second job with time 3 to worker 2, updating workloads to 3, 3, 0. Finally, we assign the job with time 2 to worker 3, giving us 3, 3, 2. Since no worker exceeds the maximum workload of 5, the allocation is feasible. Therefore, we adjust the right bound to 5, narrowing our search space. We proceed with the next midpoint, 4. The workers are initially empty at 0, 0, 0, and the maximum allowed workload is now 4. Starting with the largest job, we assign the job with time 3 to worker 1, resulting in workloads of 3, 0, 0. Then, the second job with time 3 is assigned to worker 2, updating the workloads to 3, 3, 0. However, the remaining job with time 2 cannot be assigned to any worker without exceeding the maximum workload of 4. This means the allocation is not feasible under these constraints. As a result, we adjust the left bound to 5, which leaves us with a final output of 5, since the left and right bounds converge. This value represents the minimum time required to finish all jobs with 3 workers. Now, let's consider a more complex example where the jobs are 1, 2, 4, 7, 8, and there are 2 workers available. We begin by sorting the jobs in descending order, resulting in 8, 7, 4, 2, 1. The left bound is the maximum job time, 8, while the right bound is the sum of all jobs, 22. We calculate the midpoint, 15, and test if it's feasible to allocate the jobs without exceeding this workload. First, we assign the job with time 8 to worker 1, resulting in 8, 0. Then, the job with time 7 is assigned to worker 2, updating workloads to 8, 7. Next, the job with time 4 is added to worker 1, making it 12, 7. The job with time 2 is assigned to worker 2, yielding 12, 9, and finally, the job with time 1 is also assigned to worker 2, giving us 12, 10. Since no worker exceeds the maximum workload of 15, this allocation is feasible, so we reduce the right bound to 15. We continue by testing a smaller midpoint, 11, with the workers starting at 0, 0. The maximum workload allowed is 11. Assigning the job with time 8 to worker 1 results in workloads of 8, 0, and assigning the job with time 7 to worker 2 updates the workloads to 8, 7. However, the next job with time 4 cannot be assigned without exceeding the maximum workload of 11, so this allocation is not feasible. We adjust the left bound to 12. Next, we test the midpoint of 13. Starting with both workers at 0, 0, the job with time 8 is assigned to worker 1, resulting in 8, 0. The job with time 7 is assigned to worker 2, updating to 8, 7. The job with time 4 is then added to worker 1, yielding 12, 7. The job with time 2 is assigned to worker 2, making it 12, 9, and finally, the job with time 1 is also assigned to worker 2, resulting in 12, 10. As this allocation is feasible, we reduce the right bound to 13. Finally, we test the midpoint of 12. Starting with both workers at 0, 0, we assign the job with time 8 to worker 1, resulting in 8, 0. The job with time 7 is assigned to worker 2, updating workloads to 8, 7. However, the next job with time 4 cannot be assigned without exceeding the maximum workload of 12, making this allocation not feasible. As a result, we adjust the left bound to 13. At this point, the left and right bounds converge at 13, which means the minimum time required to finish all jobs with 2 workers is 13. This concludes the solution walkthrough for this example. To analyze the time complexity of this solution, we break it into 2 parts: the binary search over possible workloads and the recursive backtracking used to verify whether a workload distribution is valid. First, the binary search operates over the range between the maximum job size and the sum of all job sizes. For n jobs and k workers, this range is at most O, sum, jobs. Each step of the binary search splits the range in half, resulting in O, log, sum, jobs, iterations. Next, we have the backtracking function, referred to as canDistribute, which explores all possible ways to assign n jobs to k workers. In the worst case, this could involve k-n recursive calls, as each job could theoretically be assigned to any of the workers. However, optimizations like sorting the jobs in descending order and pruning invalid configurations, such as stopping early when a worker has no jobs, help reduce the number of recursive calls significantly by focusing only on promising distributions. Sorting the jobs ensures that larger jobs are handled first, which minimizes invalid configurations and improves efficiency. Even with these optimizations, the worst-case time complexity of the backtracking component remains exponential at O, k to the power of n. When combining these 2 parts, for each binary search step, we invoke the canDistribute function. Since binary search requires O, log, sum, jobs, iterations in each invocation of canDistribute has a worst-case complexity of O, k to the power of n, the overall time complexity becomes O, k to the power of n asterisk log, sum, jobs. Shifting to space complexity, we account for both the recursion stack and any auxiliary data structures. The recursion stack depth is at most n, as we process 1 job per recursive call, consuming O, n, space. Additionally, we maintain a workers array of size k to track the workload assigned to each worker, which requires O, k, space. The jobs array is sorted in place, so no extra space is needed for sorting. Overall, the space complexity is primarily determined by the recursion stack and the workers array. Combining these factors, the total space complexity of the solution is O, n plus k, with contributions from the recursion stack and the workers array. Comparing this to brute force approaches, a naive solution would enumerate all possible assignments of n jobs to k workers, calculating the maximum workload for each configuration. This brute force method has a time complexity of O, k to the power of n, and lacks the optimizations achieved here. By integrating binary search and pruning techniques, our solution narrows the search space significantly. Sorting the jobs in descending order reduces the number of invalid configurations the backtracking function explores, while binary search ensures we only test feasible workload values. These improvements result in a much more efficient solution compared to naive approaches. Now, let's consider the best, average, and worst-case scenarios. In the best case, if the jobs are perfectly balanced, such as when all jobs are of equal size and can be evenly distributed among workers, the recursion tree prunes aggressively, and the time complexity becomes much lower than the worst case. In the average case, the actual number of recursive calls and the effectiveness of pruning depend on the distribution of job sizes and the number of workers. However, in the worst case, where pruning is least effective, such as when jobs must be assigned sequentially, the complexity remains O, k to the power of n asterisk log, sum, jobs. To summarize, the final big O complexity for the solution is O, k to the power of n asterisk log, sum, jobs, for time and O, n plus k, for space. Let's explore some common mistakes that can occur when solving this problem. First, Using a purely greedy allocation without backtracking might seem intuitive, like assigning the heaviest job to the least burdened worker at each step. However, this often fails to explore optimal distributions, as it can leave some workers overloaded while others are underutilized. Next, ignoring job sorting can also lead to inefficiency. If we don't sort the jobs in descending order, larger jobs might be assigned late in the process, which can unnecessarily increase the maximum workload. Another important point is overlooking edge cases. For example, when the number of workers is greater than or equal to the number of jobs, each worker can handle at most one job. On the other hand, if there's only one worker, they must handle all jobs. Missing these scenarios can lead to incorrect results or runtime errors. Lastly, improper use of binary search is a common pitfall. If you don't correctly define the search bounds or properly validate the midpoints, you might end up with infinite loops or inaccurate results. Always initialize the bounds carefully, such as setting the lower bound to the maximum job size and the upper bound to the total sum of jobs. Now, let's discuss inefficient pruning and backtracking. Skipping key pruning steps, such as avoiding redundant computations by skipping workers with identical workloads, can significantly slow down your solution and potentially lead to time limit exceeded errors. Pruning is critical to ensure that the algorithm explores only the most promising paths. Moving on to interview tips, this problem is a classic example of load balancing. The two main approaches are binary search with validation and backtracking with pruning. You'll want to demonstrate your ability to balance time complexity with optimality. It's important to highlight patterns like sorting jobs in descending order and using binary search to minimize the maximum workload. For optimization, consider techniques like early stopping when a valid solution is found or pruning paths based on current worker loads. Lastly, it's worth discussing the trade-offs. Backtracking guarantees exact results but is slower and computationally expensive. On the other hand, binary search with a load validation function strikes a balance by being more efficient while still providing near-optimal solutions. To deepen your understanding, let's take a look at some related problems. LeetCode 1011, Capacity to Ship Packages Within D-Days, uses a similar binary search approach to minimize the maximum load, making it highly relevant. Then there's LeetCode 410, Split Array Largest Sum, which is closely related as it involves dividing an array into k subarrays to minimize the largest sum. LeetCode 1231, Divide Chocolate, is another great example of a binary search problem that focuses on minimizing the maximum workload. Finally, LeetCode 698, Partition to k equal sum subsets, challenges you to distribute elements into k subsets with equal sums using backtracking. These problems share similar patterns and techniques, so practicing them can help you strengthen your understanding of both binary search and backtracking approaches. Finally, let's compare some alternative approaches and their trade-offs. Binary search with validation works by minimizing the maximum workload through binary search. For each midpoint, you validate whether it's possible to distribute the workload among the workers. This method is faster, with a time complexity of (n*log) some jobs, but it requires careful implementation to ensure correctness. Backtracking with pruning, on the other hand, involves recursively assigning jobs to workers and backtracking when the current workload exceeds the minimum found so far. While this guarantees exact results, it can be very slow, with a worst-case complexity of k to the power of n. Dynamic programming is another option. It tracks worker loads and minimizes the maximum workload, but it comes with its own trade-offs, including a more complex implementation and high memory usage. This approach is typically more suitable for smaller input sizes due to its overhead. Each of these methods has its strengths and weaknesses, so the choice depends on the problem constraints and the desired balance between speed and accuracy. Great job reaching the conclusion. Today, we tackled a challenging load balancing problem using binary search and backtracking. Remember the key concepts we covered and try applying them to similar problems. Thanks for watching, and stay tuned for more coding content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!